Welcome, everyone. Today, we're diving deep into a critical battle that's really shaping the future of the auto industry. And this isn't just about engineering, it's about who is going to define how our cars are built, right from the bones out.
So here's the central paradox, the big question facing the industry right now. We're packing our cars with all this incredible technology, huge batteries for amazing electric range, and this whole suite of sensors and computers for smart driving. But all this innovation, it comes with a pretty hefty penalty, weight. And that weight is a direct threat to the very efficiency and performance we're all trying to achieve. So just how big is this problem? Well, on average, a pure electric vehicle is over 20% heavier than a similar gas-powered car. We're talking about hundreds of extra pounds, mostly from that battery pack alone, and that fundamentally changes everything about the car's dynamics and how much energy it uses. This right here is the core challenge. To solve this, the industry is dusting off a time-tested strategy, but with a totally new sense of urgency. See, this isn't just about shaving off a few pounds for better fuel economy anymore. Nope. Lightweighting has been completely reinvented. It's now the essential key that's going to unlock the future of mobility, the thing that will let us realize the full potential of both electric and intelligent vehicles.
So, here's our game plan for this briefing. We'll break down the new reasons why lightweighting is so important, we'll assess where everyone stands right now, and then we'll dive into the three critical battlegrounds where this war on weight is being fought. And finally, we'll lay out the strategic roadmap all the way to 2040. Okay, let's jump right in.
First things first, let's be super clear. What lightweighting means strategically has been completely reshaped. It's not some secondary goal anymore. Two massive shifts in the industry have pushed it right to the center of how cars are developed. On one hand, you've got the electrification challenge. Every single pound you save on the car's body is a pound you can use for more battery, which means more range. Or you can just take it out completely to make the car accelerate faster and handle better. Then, on the other hand, you have the intelligence challenge. All those sensors, processors, and wires that make a car smart, well, they all add up. Lightweighting is the crucial lever you pull to offset that weight gain, making sure our smarter cars don't become sluggish and inefficient. So, where do things stand today? If we take a data-driven look at the competitive landscape, it reveals a really fascinating mix of big wins and some pretty serious strategic vulnerabilities. Now, this chart tells a really critical story about the EV market. In those mainstream segments, compact cars and medium SUVs, domestic brands are showing a clear advantage. Their lightweighting figures are about 20% better on average. But then you look at small SUVs, and they're lagging behind. This isn't just a number on a chart, it's a major strategic risk. It exposes a real weakness in one of the fastest growing parts of the market, mostly because a lot of these models are built on older gas-to-electric platforms. They're basically carrying the architectural baggage of a bygone era. And if you look back at the previous technology roadmap, you see the same pattern. There were clear wins in the new world of pure EVs and commercial vehicles. Goals were met, sometimes even way ahead of schedule. But huge challenges are still there in the traditional world. The targets for fuel vehicles were missed, mostly because we, the consumers, just kept wanting bigger cars with more features, and that outpaced what the engineers could achieve. Okay, so to close these gaps and really grab a leading position, the industry has to win on three critical battlegrounds. The first one is the most fundamental of all. It's about revolutionizing the very design and architecture of the car itself. A key weapon in this fight is integrated casting. So instead of stamping and welding dozens and dozens of little metal parts together, this technique casts a huge section of the car, like the entire rear underbody, as one single piece. The most famous example, of course, is Tesla's gigacasting. It replaced over 70 different parts with just one, which slashed manufacturing complexity and cut the body in weight by about 20%. It's a game changer. Another game-changing design is cell-to-body, or CTB. This is just brilliant. It turns the battery from dead weight into a structural advantage. By integrating the battery cells directly into the floor of the car, you get rid of the heavy separate battery casing and you make the whole structure stiffer and stronger. This means the car just feels more solid, more responsive, which improves both safety and handling. The BYD Seal, for instance, uses CTB to achieve a level of stiffness that rivals high-performance sports cars. All right, let's move to the second battleground, because this is where things get really interesting. See, revolutionary designs demand revolutionary materials. The very stuff our cars are made from is going through a radical transformation. And it all starts with steel. This timeline shows a dramatic shift just over the last decade. The use of traditional soft steel, it's down by over 50%. In its place, we've seen the rise of these advanced high-strength steels. And what's most impressive is the use of ultra-strong, lightweight, hot-formed steel in those critical safety structures has surged by nearly 7 times. It's become the go-to solution for creating a super strong, yet light, safety cell.
But the future isn't about just one miracle material. It's about using the right material in the right place. High-performance cars like the BYD Yangwang U9 are really pioneering this. Its structure is this sophisticated cocktail of materials. Lightweight aluminum makes up the majority, but check this out. Nearly a third is advanced carbon fiber, used in places where you need maximum stiffness with minimum weight.
And you know what? We're just getting started. The next frontier includes materials with absolutely enormous potential. We're talking about magnesium alloys, which are a full 32% lighter than aluminum, being developed for large cast parts. And new composites, like those made from eco-friendly basalt fiber, offer this amazing combination of strength, lightweight, and sustainability that's just incredibly attractive for future cars.
Okay, so you have revolutionary designs and you have these advanced materials. But this creates a brand new, incredibly complex problem. How do you join steel to aluminum, or aluminum to carbon fiber, or all three together in a way that is strong, durable, and can actually be manufactured at scale? This is the connection challenge. When we look at this table, we see a critical gap. The physical joining methods themselves, the riveting, the bonding, the welding techniques, they're globally competitive. The issue isn't the how, it's the how well. And here's where the analysis gets really sharp. Domestic capabilities are lagging in the crucial areas of performance evaluation. They're lacking robust standards to guarantee long-term durability. And they're behind in digitalization, where you have basic process monitoring up against these sophisticated, real-time online quality control systems used by foreign leaders. This is a systems and data problem, not just a hardware problem.
So this all leads to the crucial point, right? How do we win these 3 battlegrounds, design, materials, and connection, and actually achieve global leadership? This is where the strategic roadmap comes in. It lays out a very clear path to victory over the next 15 years.
The strategy unfolds in 3 distinct phases. Through 2030 is the foundation phase, all about mastering and scaling today's most advanced technologies. Then, through 2035, we have the integration phase, which focuses on deepening the fusion of multiple materials in entire vehicle systems. And finally, to 2040, we have the intelligence phase, where the goal is to lead the world with AI-driven design and completely new vehicle architectures.
And these phases aren't just abstract ideas. They have very concrete targets. For EVs, the goal is a 15% weight reduction by 2030, which will be marked by an iconic achievement like the mass production of a huge cast magnesium alloy rear floor. By 2035, a 25% reduction, showcased by something like a basalt fiber composite dashboard. And by 2040, a 30% total reduction, with breakthrough innovations like a 3D printed, biomaterial passenger cabin becoming a reality. And this brings us to our final, critical takeaway. For all the talk about software and AI defining the car of the future, this roadmap makes it crystal clear that its success will be built on a physical foundation. The innovation in its structure, in its materials, in its very bones, that will be just as important as the intelligence in its brain. The car of the future will be defined not by its brain, but by its bones. And the real question is, who will engineer them?